Welcome to the debate. We are looking today at the necessary framework for establishing a reliable, enterprise-grade AI assistant system. When a business decides to move these ambitious ideas into tangible, trustworthy AI results, the question becomes, well, where should we prioritize our effort and resources to really guarantee success? The core disagreement we'll be tackling is this. When building the technical backbone for a reliable AI assistant, is consistency and user trust primarily secured by the foundational choices, the initial technical architecture and component selection, or is it more about the continuous application of disciplined development and operational best practices? My position, fundamentally, is that reliability is determined by the quality and the scalability of that initial technical foundation. You really have to build it right from the start, or you simply cannot scale effectively at all.
Huh. Well, I come at this from a different perspective entirely. I believe that while, yes, a sound foundation is necessary, long-term reliability in an AI context, it's fundamentally a function of sustained operational discipline, robust process management, and, crucially, the system's ability to adapt and be maintained over time. I mean, in the volatile world of AI, yesterday's perfect architecture can very quickly become tomorrow's technical debt, and only disciplined process can really manage that effectively.
When we examine the foundational requirements, the necessity of a strong architecture becomes immediately clear. Look, the reliability ceiling of any system is really set during its design phase. If you failed to design for scale and robustness initially, well, no amount of rigorous testing later on can truly compensate for that potentially fatal flaw. For instance, achieving efficient context retrieval, which, let's face it, is essential for an AI assistant to be accurate, it absolutely requires the immediate implementation of advanced data structures, things like vector indexing solutions. Now, whether you choose a managed service or an open source option, the choice to integrate this kind of scalable technology is an architectural decision. It defines the initial reliability and performance under, as the material notes, heavy usage. Furthermore, handling traffic through a well-defined gateway or API layer for consistent validation and routing. That isn't just a nicety, it's the structural element that ensures data integrity right from day one. You define reliability by the components you select and, critically, how you connect them.
Okay, I agree that you need components that work, that function. But I would argue that reliability isn't merely functional, it's temporal. It's about lasting performance. The material makes it quite clear that true reliability isn't just about technology choice. It also involves disciplined development practices. And focusing purely on the stack, well, it ignores the central challenge of AI, volatility. The data powering the system degrades, the language models themselves change, the underlying APIs evolve constantly. So if you spend all your capital on a perfect initial setup, but you lack the processes to manage that inevitable change, the system degrades, and it degrades rapidly. Therefore, sustained reliability, it's secured by things like regular testing, and not just at the unit level, but rigorous integration testing to ensure components still speak to each other effectively after updates. It involves using version control systems like Git to manage the inevitable complexity, and really critically, maintaining data quality through ongoing operational cleaning and compliance processes. The process is what ensures the initial architecture stays relevant.
Right, but let's discuss how architecture actually supports process, not the other way around. My position is that the upfront architectural blueprint is what enables successful future operations. For instance, designing the system for horizontal scaling is a critical reliability factor. We absolutely must adopt containerization tools like Docker and intentionally build stateless servers where feasible. Now, these are not operational processes per se. These are fundamental, non-negotiable architectural decisions made right up front. If we design a rigid, monolithic system, it instantly complicates scaling during demand spikes. Operational discipline might help you manage the existing load, sure, but it won't fundamentally solve a structural deficiency when demand doubles overnight. The system's capacity for seamless scalability, which is absolutely core to reliability, is determined by this initial architectural commitment.
I see why you think that architecture defines the maximum capacity for scale,
But I would counter that in the context of AI, scalability might actually be secondary to flexibility. The source material demands a reliability that is intrinsically linked to dynamic evolution. It actually asks us to design architectures flexible enough to incorporate newer models as they emerge and modularize components to allow us to swap out outdated parts without overhauling everything. Now, that ability to swap components, say moving from one foundational language model to another, or maybe replacing an internal search engine, that is a function of engineering discipline and modularity design, which are both, operational and developmental outcomes. An initially scalable but structurally rigid system, it quickly becomes unreliable when the underlying technological landscape shifts, which it always does in AI. Reliability in this domain, it really means maintaining service continuity while managing pretty aggressive technological churn.
Well, we can achieve modularity through smart architectural choices like decoupling services early on. But let's pivot slightly to the core function of the assistant itself. My position holds that if the system can't perform its core function reliably, then frankly, nothing else matters much. The ability for the assistant to correctly interpret inputs and generate useful, accurate outputs relies entirely on specific, reliable technologies within that processing engine's layer. We are relying on high-performing models like OpenAI's GPT for language understanding and robust automation tools, maybe Zapier or NN, for executing tasks. If the components responsible for the actual cognitive heavy lifting, the core interpretation and generation, if they aren't stable and correctly integrated from the outset, the entire system is fundamentally broken. Operational processes can optimize delivery, absolutely, but they cannot magically create a functioning response engine if the underlying components are flawed or improperly configured. That foundational functionality must be reliable first.
Yeah, I'm sorry, but I just don't quite buy the argument that component reliability is the single defining factor here. In complex distributed AI architectures, let's be realistic. Failure is inevitable. Components will crash, APIs will experience latency spikes, models will occasionally misinterpret a query. True reliability isn't the absence of failure. It is the robust, disciplined ability to identify and mitigate that failure before it impacts the user experience or the business outcome. And this points directly to operational necessity, the need to implement monitoring tools like Prometheus or Datadog, and set up alert systems for failures. We're talking about dedicated observability platforms that provide real-time visibility into latency, error rates, resource utilization across every single layer of the stack. This disciplined practice, the operational commitment to knowing what is happening now and predicting what might happen next, that is what protects the end user experience far more effectively than the baseline reliability of any single model running at one specific moment in time. Without robust monitoring, the system is essentially flying blind, regardless of how stable its initial components were supposed to be.
Monitoring is necessary, certainly, I won't argue that, but it's fundamentally a reactive measure. Architecture is proactive. Let's talk about trust for a moment. Reliability requires fundamental user and stakeholder trust, and that, I argue, must be engineered into the architecture immediately. This means prioritizing security and compliance right from the start, not treating them as some kind of operational bolt-on later. We absolutely must incorporate robust security protocols, including encryption and access controls, aligned with industry standards right into the system design itself. Authentication must be handled meticulously at the entry layers, the user interface layer, ensuring the system is inaccessible and secure from the moment it is deployed. If the foundation is architected insecurely, if there are initial flaws in data handling or access controls, the system is inherently unreliable from the get-go. This is a foundational flaw that, frankly, no amount of logging or continuous testing can fully rectify. Security architecture provides that initial, non-negotiable guarantee of trust.
Okay, I fully agree that security is non-negotiable, but let's be precise about it. Security, especially concerning data privacy and compliance, it's a living, breathing operational burden. Look at evolving regulations like GDPR. Adherence requires continuous auditing, process updates, and data management controls that are purely operational in nature. But let's maybe zoom out to what I see as the most insidious threat to long-term reliability: maintainability. The source emphasizes the need to document interfaces thoroughly so new team members can understand how components connect. This is a purely operational and process-driven necessity. If a system is not maintainable, which relies heavily on disciplined documentation, knowledge transfer, and organized version control, it will inevitably degrade, become outdated, and ultimately fail, regardless of how perfectly secure or scalable it was on its launch day.
Maintainability fueled by operational discipline. That's the key ingredient that turns an initial successful launch into potentially a decade of reliable service.
Documentation is crucial for maintainability, yes, absolutely. But what feeds the assistant? It's the data. And the quality of that data is defined first and foremost by the initial pipelines and storage solutions, those vector databases, the data lakes that you architect at the beginning. If the initial architecture doesn't enforce strict input validation right at the gateway layer, you're essentially allowing bad data to corrupt your system immediately. While sure, operational teams must continue cleaning input sources, the architecture must provide the rigid framework for data ingress and storage that enforces quality control by design. We are talking about building guardrails into the infrastructure itself so that neverable operational lapses are less likely to lead to catastrophe.
The guardrails must exist, I grant you that. But the cleaning process you mentioned, ensuring high-quality data sets by cleaning input sources regularly, that is the continuous operational task that guarantees data-driven reliability over time. Architecture gives you the container, maybe, process cleans the contents, and data bias, data drift. These are dynamic problems that evolve as the world changes. No static architecture, however well designed, can prevent your initially pristine training data from becoming irrelevant or biased 3-6 months down the line. Only the disciplined, continuous operational practice of monitoring, cleaning, and crucially retraining can guarantee the long-term reliability of the assistant's output. That sustained effort, that is the actual source of enduring reliability.
I certainly acknowledge the absolute necessity of disciplined processes, the rigorous testing, the meticulous documentation, and crucial continuous data pipeline management you advocate for are vital components of any successful rollout. However, consistent performance, the ability to handle growth, and providing that initial high level of engagement that the source material emphasizes, which really accelerates user adoption, that requires us to commit heavily to the upfront architectural investment. Choosing scalable cloud hosting, integrating specialized technologies like vector indexing solutions early on, and engineering components for statelessness, these provide the necessary foundation for high availability. That initial robust architecture really sets the maximum potential for the system.
And I agree that the foundation must be robust. If the architecture is built on quicksand, the whole structure will eventually collapse. But the goal here, as stated, is reliability that transforms the AI assistant into an indispensable partner that employees trust and genuinely embrace daily. That kind of long-term trust, I maintain, is secured by continuous iterative practices, rigorous quality assurance, effective version control, and perhaps most critically, the architectural and organizational flexibility required to handle the inevitable technological evolution and data decay. A perfect initial design is merely a starting point. It's the disciplined operational ability of the team to maintain, update, and evolve the system that ensures true, lasting reliability.
Well, it seems clear that reliability is definitely a multifaceted construct. It's critically dependent on both those engineering decisions made right at the start and the processes applied consistently throughout its entire lifespan.
Indeed. The real tension probably lies in the resource allocation and the maybe philosophical prioritization. We have to recognize that while a strong technical framework is certainly the prerequisite, it's those disciplined operational practices that provide the indispensable longevity required in the complex and frankly ever-shifting landscape of modern AI systems. There is certainly much more to explore in how these two areas interact dynamically during the often resource-intensive implementation phase.